Alright, so today's topic, we're going to talk on pointers. Once again, the book puts this back chapter 6, and they deal with it some more in chapter 13. They don't really do much with it in chapter 6. And some of the things I've seen that they had in the notes and everything to talk about and everything, they were using pointers just for the sake of using pointers with no meaning to it. I have never dealt with pointers in that aspect, and so it was kind of some meaningless stuff. So I wanted to save that topic till now, when we can actually do some more in-depth stuff with them. Because this is where you actually be using the pointers. Now, of course, trick comes, let me turn this on, it might help. What is a pointer? A pointer is going to be a data type, like they're describing anything else, but a pointer is a memory cell that stores the address of a data item. Doesn't really say much, but yeah, do remember the definition. You'll probably see it again, at least once, maybe twice, because the final is cumulative. But if you're declaring a variable, we have an integer. We'll call m. Of course, this is a data type, and he gets a little spot in memory out here we call m, and he can hold whatever we put into it, right? Well, a pointer is a memory cell that stores the address of a data item. So he's got a location out here, and we're going to call him an int pointer using the asterisk. We'll just call him T. So T is here, and he holds the memory address. If I do this, T equals address of M. He will hold the memory address of M. So wherever in memory M is stored, that's what gets stored in here. So 1024. That's where he is. Now, of course, it didn't. Why would we need to have T holding the memory address if we can still call him M and get to him anyway? It seems a little redundant, doesn't it? It just gets a little confusing. Now, once again, right here, we know from doing our scanf statement, doing that ampersand M guy on there, you get the address of M. So when you want to scan and stick stuff into M, you have to have his address. Well, guess what? When you're doing that, you're actually dealing with a pointer. And we'll look at that here a little bit more. So when you're declaring a variable of type pointer, in this case it's an integer pointer, you use that star, asterisk, as your pointer notation. Okay, so once again, this shows here what's going to happen. We have an integer pointer temp, or itemp in this case. M with 25. It's once again pretty much like what I wrote on the board, but now it gets graphical up here doing it. Itemp equals the address of M. So whatever memory location M was, once again, that's what's getting stored in itemp. So now itemp points to M's data. Does that make sense so far? No. That's what happens when you come in late. Alright. Now you use the asterisk to reference the memory location's data. If I want to get to that using itemp, the star itemp, asterisk itemp, that's actually, we're talking about the 25 now. You've got the pointer to him, itemp is the pointer, star, and the name pointer, is the data at the other end. It's got to access.
So it's going to be 2 times 25?
Correct.
50?
So do that. beep, and it just changed it to 50. So it's pointer itemp equals 2 times pointer itemp.
So is this kind of where I was going, or what I was thinking of when we were doing that receipt, and I was trying to do a line by line change as opposed to rerouting the whole damn thing? You can create a pointer file for...
Maybe. We'll get into some more of it here in a little bit, and hopefully you'll understand. Alright, now, where have we already seen pointers? Guess what? Our file pointers, we've dealt with some pointers before with files. You just didn't really understand what was going on at the time. You still probably won't understand what's going on when you file pointer. But when you open that text file, it creates a link in the memory out here to that data on the disk. That file is out there. So now, in this case, FP on the memory address that is linked to that file. That's going to create a buffer out there for writing data into and pulling data out of in memory from that file. And that's what you're dealing with the pointers there. And once again, our old scanf buddy here. When you're calling scanf, passing it this, and the address of the data, well, guess what? The way that the function is defined, we never see the definition of the scanf function. We just have been using it. Let's say we created our own function that's called change it here. And we're going to pass it two variables, x and y. And we want them to do something to x and y and pass those back. Now, previously, if we had wanted to do something, we could call a function such, in this case, like do it, x and y, and if it's an integer over here, using a return type, it could do something, add x and y, divide by whatever, and then return whatever value we want it to return to come back this way. But it only returns one value. So what if we wanted to do something, and we could say, like, in this case, x equals do it xy. Well, that will change x as it returns back. But if we want x and y both changed, we can't do it like this. But if you do here, passing it int pointer x, int pointer y, in this case we call it, what we're doing here, we call it, we're actually passing m and n to it. Internally in the thing, it's going to call it x and y. But by passing the addresses of these guys, because it's needing pointers, you pass the addresses. That's what's going in to it. Now, anything that happens within change it to m and n, are actually anything internally happens to x and y. Changes m and n on the outside. So, normally the scope, and once again, switch that. In this example, that should be m and n. Let me draw that up here a little bit. Okay. In your main, you've got m and you've got n. You're calling change it, passing it the address of m and the address of n. Down here you've got the actual change it function, which is needing x and y, and the pointer x, anything in here, you know, he's got X and he's got Y in him. Now I can talk about the scope. M and N, what is their scope? Only within here. X and Y scope is only within here. But by passing it in here, the address of M, X is now a pointer to the original M. He's actually going to mess with that memory location. And by passing address of N into the Y pointer, Y is a pointer to the original location of N. This is called passing variables by reference. You're referring to the actual value you were talking about before. What happens if what do we call it if we send it without the address things? That makes a copy of it. So you have a totally separate X and a Y than you had from the M and N. They just get the value of those copied in, not the actual location. So that's the big difference. Using the pointers and the addresses, you're passing the actual reference to the real guys up there. So now you can change more than one thing if you're needing to. Any questions on that? All right. Now we get to have our real fun. Start doing some linked lists and some other data types. Now there's a whole different class that would build into this. That's going to be your data structures class. This is kind of a precursor to what you'll see in 1437. The next class up. So once again, I am teaching that for the fall. So if you like me, feel free to sign up for my class.
Who's teaching it in the summer?
I have no idea. I don't know if it's being taught this summer.
It is.
Is it? And maybe Kate Pleasant. She's one who had them doing stuff. All right. Arrays. We've got arrays out there. What's the limitation of an array? You have to know the size of it at compile time. So when you make your program, you've compiled your program, you're going to sell it to somebody. If you use an array, it's only going to be good for a certain size of data. And you have to know that size to start with. Now you could declare your array of size 100,000 just in case. Well, what's that going to do?
Eat up a lot of memory.
Yeah. Someone who only has 10, that's wasting a lot of resources. You know, Windows is already fighting this stuff, right? So that's the drawback of using an array. How do we get around that? Well, we go over to our linked lists. And then our binary trees. So as we talked about linked lists and binary trees, these will be guys that you will see on this next test. Remember when we did our bubble sort stuff and you had to figure out how to do some stuff there? Pay close attention to linked lists and binary trees because you'll be doing some stuff with them on your next test. So let's say a linked list. What we're going to do here, well, we start off with a struct. Let's start off with a struct. And this one we've got a person. So, and we're going to keep track of some different things about a person. I have their name, their age, their social security number, and then there's a thing in here that's a person pointer next. So each person has a link to another person called next. Any ideas what it's going to do? What we're looking at is, we go out there, we wind up with one piece of this data. Okay, we've got our name, we've got our age, we've got our social security number. I'm going to draw a little, actually, I'm going to draw it like this. And there's a pointer to next. Say that pointer, hey, there he is. Stick it out here. And guess what? We can chain these guys together. And he's got his pointer to the next. He's got his pointer to the next. Until we get to the end, and he's got a null. I'll just write that up here. Null. That means nobody else. He can't point to anybody else because there's nobody else out there. Alright, see the advantage of this? You need a new one, just come to the end, stick a new guy out here, stick this guy to point to him now, put him to null, and we've got a new guy on the end. And so we can keep whatever data we need about him and point it to next. Now another thing about this is when you did an array, it set up all that contiguous memory out here together that's been tracking these with. Out here, these guys can be all over the place. He grabs just enough data for this guy over here. Next time he grabs some more data. It could be consecutive, whatever the memory manager of the computer is returning as it's requested from the operating system. Nope, but there's no more contiguous memory. It's already taken with something else. No, I'll just go over here and grab a piece. Another piece. Oh, I'll just go over here and grab a piece. Until it fits in with whatever memory is left. I can just keep grabbing little pieces all over the place. And those pointers are just like, hey, next one's over here, next one's over here, next one's over here. So you can chain all over the place here. That doesn't matter to you. You just, hey, go to the next one. Yeah, come here now. Alright, so once again, there's like what I just drew on the board. What's the next element in the list until you hit a null. Alright, so what do we need to do to create one of these? Alright, let me wipe off this part. We'll keep our linked list going across the top here. And we're going to need to move through our list. We're going to need to know a few things. We're going to leave one pointer pointing here to the head of the list. So we'll want a head pointer. How would we need to know the start? And we've got to leave him here at the start. Because instead of having a variable that references him, okay, we had M was 25 over here. We could reference him by M. We've got our linked list up here. Where's he starting? Or wherever head is pointing. And you ever lose track of him, you move head somewhere else, you have no way to get back to him. You've got to keep something, because head's going to be a variable that's going to hold that starting memory address. And now we can move things around, but if you ever lose track of who your head is, you can never get back to it. But if we know the head, we can traverse down to anybody else. Just taking the steps to do it. Now, once again, this guy can grow as we need. We just keep adding to him, adding to him. What's going to be handy to know if we're going to keep adding to it? Exactly. Where's the tail right now? The end, so we can come and add to that end. So we're going to set up a pointer to tail. And so, processes that you'll need to do to a linked list. You've got to be able to add to it, right? So here's your syntax for adding to the tail. to any linked list. Okay, we're going to go create us a new person first. Which is, we go out, we say, hey, person, new person, that's a person pointer. So once again, person is the data type, our struct. New person is the variable name that's going to point to it. All right? Here's the command right here, malloc. Malloc is short for memory allocate. That's what's going to give us the memory we need. It says, hey, operating system, give me a chunk of memory the size of a person. So, depending on what I just got in person. Remember, we had a string for the name of so many characters. We had an integer for the age. We had a string for the social security number, and then a pointer to another person. So the size of a person pointer and those 3 data items. Let's go here. Oops. Right. Okay. Back to the program. Here's your chunk of memory. And we did a little typecasting here, turning it into a person pointer. For the, because it's going to return the address. Malloc returns the address of this memory type. He says, okay, there it is. Okay, we're going to change that to a person pointer and call it new person. So there's a chunk of data sitting out here, right? A chunk of memory ready for us to fill with data. So then we can do our stuff on new person.name, or new, once again, here it'd be new person. Actually, we do this for the video. Can see me. New person. And the little arrow guy, name, equals whatever we want to equal. New person. So, what was our other guy's SSN? Equals whatever we want that to be. And new person. Age equals 23. And don't forget your semicolons and end your sentences. Now, we don't want him to point to anybody else yet, so we're going to say his next equals capital letters null. That says his little guy out here, he's not going to point to anywhere. Alright, so that gives us the new guy. And he's just floating out here. Then we have to decide what to do with it. There's 2 different cases that can happen here. If we already have an existing linked list, we're saying you take the tail. The tail is pointing to the last element in the list, right? And so you say tail dash tail point next. So we'll say this guy right here. This is our next. All these guys. That's his next. We're going to take him. He equals new person. So whatever new person was, that memory address stored in new person that pointed to this chunk. That's what we're going to store in here. We're going to store that memory address right there. So now, tail's next points to this same chunk of data that new person's pointing to. Then we say tail equals tail's next. So whatever next was, we're going to move tail down. Tail is now going to point to that block rather than this one. And that's, well, I already took care of it right here. If we didn't take care of it right here when we set the other data, you'd set it now. So tails next is null. And that's how you, 3 little lines to add a new guy to the end after you've created it. Now, the fun part is, what if you don't have any linked lists yet? Well, you have your head and your tail out here waiting. See, I'll put them up here. Head points up there. All right. But as so our new linked list right here. Is there another one of these? Doesn't look like it. All right. If no elements yet exist in the list, you've got head and you've got tail. Right now they don't point anywhere, but they're pointers out here just waiting. So the first thing you do is you go create your new block of memory with your memory allocate, and you say head is the new person, and you say tail equals head, which also then will point to new person, and tails.next is null. Ding. Okay, there's the start of our linked list. He's one link in the chain. From there, then when you add, that's when you would move the tail. So tail equals, you grab another chunk, set tail equal to tails next. Actually, you set, first of all, his next to point to the new person. Then you say tail equals tails next. So tail moves over here. That's what you just keep doing. You say, okay, grab a new chunk of memory, set his next to point to him, and move your tail. Just keep remembering to move your tail, move your tail, move your tail, right? And we'll get there. It must be being pretty boring today, or people stayed up late last night finishing projects. They're sick. Why aren't you sitting on the back then? How's your player affecting me? Alright, so you get how to add to a linked list. Yes? No?
What's that?
Do we get how to add to a linked list? Does the linked list make sense itself first? Do we get linked lists? The purpose for it was going to keep growing. Anytime you need new data, just add to it. Keep growing. All right. Removing elements from the linked list. Oh, let me see real quick. Okay, yeah, I'm going to get to searching on this here in a minute. So we want to take somebody out of the linked list. Why would we want to take people out of the list? They're just storing phone numbers. That's one thing. You know, you're probably going to have something better than a linked list for storing your phone numbers and stuff in. But something good for using is if you're emulating a line. You're keeping track of people coming online to buy something, and you want to make sure they get it in the right order, like concert tickets. You want to get the last person who logs in to get the best tickets. But wait, there's people who's been waiting on here 30 minutes for their chance. Or like people lined up at the bank, or at Six Flags, waiting for the roller coaster. You don't want to just start pulling people out of the middle of the line and putting them on the ride, right? You've got people adding to the line, so you're going to grow the line. And who gets on the ride? Only the people at the front, right? So you take people off the front, And then you add more people on, you take people off the front, you add people on, take people off the front. It's a FIFO queue. First in, first out. So get used to the words FIFO, you'll be hearing them the rest of your computer science career. Because it's something that you get to process a lot of. Because you're dealing with that. How many of y'all have ever burned a DVD on your computer? In the days now, you don't have to worry about it as much. Used to, you had to worry about buffer underruns. If it was writing data faster than it was putting data in, we would have a buffer. Once again, it's a chunk of space that would put data into this spot to be burned, so it's ready. The burner is always pulling from this end, and you're adding more data over here as it keeps burning. And hopefully you're not still processing. If it gets to this point as it's burning and you're still right here putting data and it burns that data, well, its burner needs to run constantly. And suddenly you ran out of data, it reached the end, no more data. Either your disk is now done, or you have a coaster. That's what we call it. Or a frisbee, or whatever you want to call it, because it's not going to work anymore. But using like a linked list and a thing here to store that data, you've got a buffer of data. Adding to the end, pulling from the front in a queue. So, the way you want to do this, let's see, I believe I've got an animation here in a minute for that. Alright. Okay, I showed you what to do, pulling data off the front. So we'll use my example that's already on the board up here, our person queue. If we're going to use this chunk of memory right here, and be done with it, and be ready to move on to him for processing. So we're going to create a temp pointer. So a temporary guy, his head's still pointing up here. So we create temp. Temp equals head. So wherever head points, temp is now pointing. Head equals heads dot next. The head moves up. He's not there anymore. And we say free temp. Whatever piece of memory that temp is pointing to, free it up to be used somewhere else. He's been returned to the operating system for reallocation. We still have our head pointing here. Now, what happens if we forget this step right here? Head equals heads next. Well, let's go back. We're going to undo real quick, which doesn't work. Okay, temp is here. Head is still pointing here. We say free temp. All right, head equals heads next. Where's heads next? We don't have him anymore. He doesn't exist. Now how do we get to these guys? We don't. Because this guy right there was the only guy who knew who was next, and we just killed him. So you do that out of order, you lose all your data. So you got to make sure, yeah. Keep a tip pointing at him, move your head, then kill the tip. Handy things to know, you'll probably see again on the 24th. So that's how you work on taking people off. We can add to the end. We've seen how to add to the end. See how to take away from the middle. Right? Take away from the front. Processing the queue. All right. Now searching the list. There's somebody out here that we want to find. We want to find out William's name. And we want to find out William's age. Let's say we want to find out William's age. Well, we know his name. So we can start off here, start off at the head, and we compare. Okay, temp is pointing at head, head is now over here. Remember, we decided we're going to delete the other one off properly. So we do have head pointing at our first guy. We start temp off, pointing where head points. Then while, we can't say while temp's name not equal to target name, can we? That's the try arrays or strings. So we've got our special little guy, string compare. So we're going to compare the name of the person here that pointer is pointing to against the target name. Is this William? Oh no, this is Al. So the Al, Fred, William. Okay. Found William. He's over here. So once again, string compare returns either a -1, a 0, or a +1, depending on where it is alphabetically. Remember? So while he's not 0, we say temp equals temp's next. So we just move temp up to him. And we check again. Is temp, the temp's name equal to the target name? No, that's Fred, it's not William. So temp equals temp's next. Here we are. We test. This is William. So that's what you'll do. You go through, just like you'd be doing a for loop or something, going through an array, checking for the array values. This is the way that you traverse a linked list. Just keep going until you find your guy. Instead of saying instead of saying name sub x, doing x plus plus to move through and then temp that next. Move. All right. Questions? Not temp, not next. Temp equals temp's next. And that reassigns temp to the next guy in the list. Okay. Questions? Yeah. I've seen some quizzical looks on faces. So. Okay. Got that far? Alright. Now we're going to do a little bit more difficult guy. We're going to remove something from the middle. Now, we are going to be a little bit more graphical on this one. We're going to let the guy up here do our work for us. So I'm targeting this guy in the middle here to be removed. See, they're all nice and linked. We've got a head and a tail. So what do we do? So first of all, you go through and you find the guy you want to remove and set a temp pointer to him. I'm saying temp 1 because we're going to need another guy. Because if you look, if we take him out of the picture right now, what happens?
Lose the rest of your links.
Exactly, we lose everything after it. So what would we have to do?
Reestablish your
See, well, if he's the only one right now that's got this address that points down, where do we need to put it? Who needs that address now?
Well, forward.
Yeah, the one over here, or before it. So, we're going to find the element before the one to be removed. And set temp 2 to point to him. So, just say if, what you do is you're moving temp 2, so you can start at the head with temp 2 or something and move him up until temp 2's next equals temp 1. So if his next right now equals the same thing as temp 1, you've got the right guy. So that's temp 2. Temp 2's next equals temp 1's next. See what we just did? He was here. Now he points to the same place that temp 1 did. Then we free temp 1. Poof, he's gone. That's what we're doing. Anyone need another step through? Temp 1 to the guy, temp 2 to the guy before him. Now you could do this while you did your search. If you're trying to find the right guy, start off with temp 1 and temp 2 at head. Move temp 1 up. So okay, well, if we need to go again, we move him up, move temp 2 here. Move temp 1, move temp 2. Move temp 1, move temp 2. Okay, found it. So you can just do a little double step when you're moving temp 1 to find. Just bring that temp 2 right up with it. Make it a little easier on you. And kill it. Alright, so what new instructions do we have that we're going to use to create a new chunk of data? Yeah, memory allocation. Short is what? malloc. So that'll be a new word for you, malloc. And you do that, he takes the size of the data structure you're using. He's going to return the address of that size that's been set aside for you. How do you get rid of a chunk of data? Free, that's right. So you allocate it with memory alloc, malloc, and you just free to get rid of it. They should have used deallocate or something for like deallocate, in my opinion. It would just match. Free, that works. All right. Now we're going to get a little bit more involved with a binary tree. And this is actually what lab is going to be this week. We're going to let you play around with a binary tree. But actually, it's more than 1 week. This is your final lab, and you'll get like 2.5 to 3 weeks to work on it. However long it is until like 1 week before the final. You can turn this one in. All right. This one, we're actually going to play a little game with this one. From a binary tree, you get your little chunk of data up here, and he's going to have 2 different pointers on him. So he can go out. So this, you got to have your root here, your root node on him. You can still call him head, whatever you want, but he's the top guy. From there, let's say in this case, we can have like a name. And then we've got, I'm putting 2 pointers here, yes and no. You can also do a thing if you're putting numbers in. You have a less than and a greater than. What's going to happen here is we're going to come up later and we're going to add some more nodes on. And depending on what this is, if it was a number, you say like 7. And this one's saying less or more. And I've got the number 7. And I come up with the number 2. Well, is 2 less or greater than 7? All right, so he's less. So we let 7's less pointer point to 2. I'm trying to decide if I got this right. Actually, we actually build the other way. We actually build the other way. So we had 7. And we created a new one that's 2. We decide from him was the existing one less than or greater than this one? And in this case, it's greater than. And now his are set to nulls. He has nothing after him. So we create another one that's a 5. Well, it's 2 less than or greater than 5. So he's less than the 5. So So we can keep on doing things like this until we can sort out data. But you'll wind up with things that will come down. You have a possibility of doing this, almost like a family tree, too. Because each person has a grandmother and a mother and a father, and okay, their mother and their father, and their mother and their father. Your family tree being a binary tree, meaning two to go from, like mother and father, you know, yes or no, true, false, things like that. All right. Now, what we're going to do with it, playing a game, is we're going to have a guessing game. Okay, we've already done a thing before where the computer guessed a number, chose a number, and you had to guess what it was, right? Well, this time, we're going to let the computer guess what animal you're thinking of. You get to think of an animal, and the computer gets to guess. Sounds like a little artificial intelligence, doesn't it? So, let's have some decision things to go through with it. So first of all, we're going to create us a node. And we're going to have our struct. We have an animal. But we're going to have, the data parts are a question, we've got yes and no, which are pointers to more animals. I'll just put a pointer. A question is a string, so it's a char array. Okay? So that's what our blocks of data out there is going to be. It's going to have a question, and then a yes, and a no pointer. Getting a dead guy here. So what we do first, and once again, this is what your lab is basing off of. So this is a very good resource to go off of. This has already been uploaded to Blackboard, so it's there. All right, so we're going to create a new head and stick him pointing to our new node. You get to do this to start with. And you've got some variables out here of our answer. We have more pointers to animals, so it's current and previous. Right now, they don't point to anything. Okay, head's question says an elephant. So that's what we're going to store in here. We're going to say elephant. And we're setting his so his pointers will be null. So they're not going to point to anybody. So he's the end of the line. That's actually what we're looking at. He's the bottom node. So we come up and we say, okay, the computer's going to prompt you, think of an animal, then press enter. It's going to set the head and the current and the previous the head. Okay, got that? See what's happening? We've created one node that's got an elephant in it. The current and previous point to him. So you think of an animal. And then it waits for you to hit enter. And he says, at this point he comes up and he says, current question. What is current question? Actually, in this case, it's the actual name.
It's going to ask you if it's an elephant.
Yeah, so he's prompting you. Think of an animal, and hit enter. You hit enter, and he says, elephant. And you ask for your answer, yes or no. Was I right? Was it an elephant?
No.
Well, if you hit yes, that's an easy one. Yay, I win. See, right there. So if the answer is yes, and current's yes answer, so remember there's yes and there's no. Pointers to more guys. If it's null, there is nobody else over here. So if you answered yes and there's nothing else on the yes branch, hey, you got it. But let's say you answered no. It's not an elephant. Well, he's going to learn from this. Oh, because he doesn't know anything else. All he knows is an elephant right now. You're going to teach it. He says, okay, I give up. What is it? And you type in your new name of what you want. And we're going to go out. We're going to create 2 new memory locations. Here and here, if the marker worked. Still not do it. Okay, so you see 2 new memory locations. And we're going to say, okay, now type a question that would differentiate a, whatever, what animal did you think of?
A unicorn.
A unicorn.
Yep.
All right. So we're going to have a unicorn. And it's going to type a question that differentiate a elephant from a unicorn. What differentiates an elephant from a unicorn?
Magical rays of sunshine.
All right. From there, you'd have, well, we just stick to the horn. But you'll see it later where that will come. So, we've got one guy pointing to the question and one guy pointing to the new animal.
Well, elephants can have horns and called tusks.
Okay, all right, so it scans in your question. He says new questions thing will be, does it have whatever? And he says, okay, now the answer for a unicorn, thank you. Oh, see why I'm not on the basketball team. All right, now we've got our question, we've got our new animal. We say, does it have
Wings.
wings? We'll say wings. There we go. All right, it says, okay, what is the answer for a unicorn? Is that the yes or the no? From you, I would think the unicorn would be the yes. And we scan that in. All right, so it says now, if there's just no question answered as a yes, we're going to say new questions yes equals to new animal. So he's going to point to him. And the new questions no will point to whatever current was pointing to. And previous is yes.
Goes back to
Equals
yes,
current. So current. So previous is yes. Well, see, he doesn't have anything else here. Yes. Equals current. Well,
Still go back to
right
you.
now, previous, yeah, since this was the very first one, there's a little bit of trickery you need to do if it's the very first node.
Any animals, yes, would be a winner.
Actually, we don't want to set previous to anything yet. These up here, we'll make previous is yes equals new question. Yes. Right now, previous was set. Okay. We want that only if he's not the first element. Only if he's not the first element. All right. New animal. Yes. Is null. And is no is yes and is no or null. And well, by the way, I probably left out the stuff that said oh no, there it is, string copy, new animals question, true. Unicorn. It's over here. All right. So there it is. So what happens next time? We come up, and we'll probably ask you, do you want to play again? So, okay, we're going to play again. So we're going to reset our current up here. And we don't do anything with previous until the, actually, when we got a new question, we want to move head if we have to. So he's going to be our first guy there now too. So next time we play, since it'll tell you think of an animal. Okay, you think of your animal?
Yep.
Now he's going to show us. Yeah, he's going to point out right here. This is part of our loop for playing again. So he comes back up here to head. So we can have, actually don't have previous as head yet. We'll only change him if we start when we start moving through. All right. And as soon as you think of an animal, he's going to put out there heads. Actually, well, this is current. Current points to head. The current's question is going to pop in there. It says, does it have wings?
No.
No, it doesn't have wings. So the no says, elephant?
No.
And he just said no again. So, okay. In that case, we're going to stick out here a new question. Right? Is it okay? He'll come up and he'll say, I give up. What is it? Because he hit the end of the line and hit the null here. That's why he said no, and there's nothing else to go to. Okay, so what is it?
Alligator.
An alligator. Okay, we're going to string copy that in here. I said, okay, what differentiates an alligator from an elephant?
It's got scales.
Scales. Okay, oh, by the way, it has a question up here. It says scales. There's a yes and a no. So it says, oh, by the way, yeah, we've copied our previous to him at this point. You'll see why. Here. All right. What is the answer for an alligator? Yes or no? Does it have scales?
Yes.
Yes, it has scales. So yes goes alligator. And now we're going to say new questions. Yes, that's the new animal. New questions no points to currents. Actually, got a little backwards on this one. So this is the part you have to start mapping out to do. It needs to be currents next, and currents no. Or
On the logic.
yeah, that's part of the logic we have to work out as part of your lab. My brain must have gone to sleep when I was thinking on this part. I was getting interruptions at the time I was plotting it out. So he goes here, scales no. Elephant is what he needs to point to. He needs to point up to here. And this will change to that. So it's that kind of logic you'll have to work out. Because programming is logic. That's the whole thing. What do we do for what? And so you're going to be changing these yes and no pointers based off of this. And what you'll wind up with eventually is a series of questions and finally at the end you will have your animals that won't go anywhere else. Now there may be more questions off to the side. And you wind up with your final notes. So, that's a binary tree. So, we will work more on this part, try to work out that logic that we'll need for that properly. See how to, what we're going to have to write as far as we'll adapt this to fit this. So once again, those in my lab section, this is what you're going to be doing for the next 3 weeks to get working for you. And so last time we'll meet together for lab will be this Thursday. You might just do it and turn it in or meet with me on questions or email it to me with questions and stuff. All right. Did I confuse you enough with this? Well, it's meant to. It's a puzzle. All right? It is a logic puzzle. It's a game. So think of figuring out how to do it as part of a logic game as well. So that's part of trying to figure out. So if you want, go ahead and start figure out what you're going to have to do to move, because you're going to need to hold a place so that you can change this to here, without losing something. That's the trick. You got to figure out how to move these pointers without losing things. But you'll have a game when you're done. And so that'll be your second game you got to write in this course. I think one of the things I asked you the first day, if you're expecting to write games by the end of the class, right?
There's already a game that does this. You just got to get the code from that.
Well, it's going to be in C and using a binary tree.
So I don't know what it's in.
And yeah, there's plenty of games out there that do for things like this. I'd say one of the ones that was fun to go with too, based off of things like this, one of the first computer games was actually a program called ELIZA. E-L-I-Z-A, I believe it was. And it was a psychoanalyst program, which you sit there and type to and say, hello, well, how do you feel today? And whatever you answered, it would pick out certain keywords off of your answer and then flip that into some kind of question. Do I feel rotten? Well, why do you feel rotten? Well, I stubbed my toe on the table. Well, why do tables make you feel bad? Do you have something against the table? And so it would take and just pull off these things, and you just keep interacting with it based off of words it was pulling. And so that was the actual start of artificial intelligence. Because guess what? Now that you do Siri's the exact same thing now on your iPads and everything.
Siri almost makes me throw my phone out the window every time I talk to that. I'm just saying.
They've come a long way, but once again, it starts with something like this. So somewhere in the background, Siri has something going with these little branching things. So whatever you do, it figures out. So, looking forward to some more fun. All right, we will see you Thursday.